Okay, so today's notes are on piecewise functions. Our content objective is to graph, write, and apply piecewise functions, and our language objective is to correctly define and identify piecewise, step, and greatest integer functions. So the first thing I did here is define piecewise functions. So piecewise functions are functions that have different rules for different parts of their domains. So that means, as you can see down here in our first example, I've asked us to graph this piecewise function. It looks slightly different from our normal function equations because I specify what the rules are for different sections of the domain. So you can see here are the sections of the domain. Here are the rules for those sections. So this is what a piecewise function looks like written out as an equation. This part is not part of the piecewise function. This is just a reminder of our slope-intercept form. In case you've forgotten, y equals mx plus b, where m is our slope, b is our y-intercept. I bring that up because we're about to graph these linear functions, and I want you to keep in mind what they would look like. So I already started sketching this function below, so I'm gonna reveal it to you under this poster. The first interval is when x is greater than or equal to 0, and the rule is 2x. So that means that my slope is gonna be 2, and my y-intercept, since there's nothing being added on, is going to be 0. So my slope is 2, my y-intercept is 0. So that's the first one I sketched here. I started at 0, I counted up 1 over 2, sorry, up 2 over 1, up 2 over 1. Drew my line, since it's everything, or it's going to continue on forever, since it's everything when x is greater than or equal to 0, I can draw an arrow on the end because it's going to continue on indefinitely. The second interval is only from 0 to -2. And it's a slope of -1/2 x. So again, there's no b value, so I'm starting at 0 again as my y-intercept, but I'm only going to go up 1 over 2 in the negative direction. And since it's only for that small interval, I'm going to stop there. So I'm going to stop right there for that interval because it's only for those two places that it follows that rule. The last rule is x plus 3. So again, my slope here is 1, my y-intercept is 3. So I'm going to go up to 3 on my y-axis just to get a reference. I'm not going to draw a point there because my domain doesn't start until x is less than -2. So I'm going to follow my slope of 1. So I'm going to go down 1 over 1, down 1 over 1 until I get to -2. So that's right there. Starting at that point, I'm going to draw a slope of 1. So I'm going to go down 1 over 1, down 1 over 1, and then my line will continue on that way indefinitely. So again, notice that I didn't start actually drawing that line, even though I started counting at my y-intercept. I didn't draw my line until I reached the part of the domain where that started. So that would be the graph for this specific piecewise function. So the key things I want us to remember when we're doing this, we graph each section individually. And I want to make sure you're paying attention to what points. Note the endpoints or bounds of your intervals. So those are going to be important when you're graphing as well. So I want to do a quick check if you want to try this on your own. I want you to try to graph this as much as you can by yourself. I'll make it a little less complicated. So I want you to graph f of x is equal to -x plus 1 for x is greater than 0 and 2x minus 2 for x is less than 0. So try this one on your own. Pause it if you need to. I'm going to go over it now. So I'm going to give myself a little bit of room here to do this. I have my x-axis, my y-axis, 1, 2, 3, 1, 2, 3 is down here, 1, 2, 1, 2. All right, so this is my general grid real quick. And I'm going to start with this rule. So when x is greater than 0, so I'm doing this side first, I'm going to start at 0, and I'm graphing the line -x plus 1. So I'm going to go to plus 1. Since it doesn't have the equals to line, I'm going to put an open circle on that value. where it starts, and then I'm going to go down 1, over 1, down 1, over 1, down 1, over 1, and I can draw this line. It's going to continue on indefinitely because it's every value above 0 in the domain, so I can leave it with an arrow and I'm all set. The next one, it's 2x minus 2 for x is less than 0. So again, I'm starting at the same value, but I'm again going to have an open circle since there's no line underneath. So I'm going to go to -2, and I'm going to make an open circle on my y-axis. And then now I'm going up 2 over 1, up 2 over 1, and my line looks something like this. Again, it goes forever in that direction, so I can leave an arrow on that end. And that's what my piecewise function looks like. A little bit weird, I know, but that's what piecewise functions can look like because it's different rules for different domains, so they can look kind of choppy like that. All right, the next thing I want to talk about is writing a piecewise function from a graph. So I'm going to flip the page for that. So for this one, our example, I want us to write the rule or rules for the piecewise function below. And since you guys have to bear with me while I graph it, you might get some hints as to how to do this. But we're going to draw this line here, and then that line. So I'm going to go 1, 2, and then 1, 2, 3. That's -3. That's my y-axis, my x-axis, and then I'm going to go 1, 2, 3, 1, 2, 3. Okay, and then my first one is going to go to -2 and draw here. That's an arrow on the end, sorry. And then I'm going to draw a point here and here. And then last but not least, I'm going to draw a point here. Draw that. Okay, so try your best to try to write the function rule for that graph. Do the best you can. Sorry, I don't have the best drawing skills. But I'm going to go through the steps for this because I think it can be a little bit trickier. So the first thing I want us to do is identify turns or changes in direction. Or breaks if that's helpful. So I'm going to write our function f of x equals our little brackets, and then I'm going to leave some space to write the rule, and I'm going to write the domain sections, but after identifying the turns. So my first two steps are going to be identify the turns and then write domain intervals. So again, my turning points, if I circle them, are here and here. So I know that my domain intervals have to include before this, between these, and after that, because those are the points that I have changes in direction. So I'm going to have 3 different intervals, which is why I drew my curly bracket, including 3 lines. So the first one, I'm going to say is going to be when x is less than, and this is 1, -2. I'm always going to go from least value to, when I'm drawing these, if there's no open circles, I'm going to put the equals to sign on the one that comes first. So x is less than -2 comes as my first interval, so I'll put the equals to sign there. Sorry, this should say 4, and then the comma goes before 4. The next interval, again, has to start at -2, because that's where my last one left off. And then it can't include 2 because then it wouldn't be a function if it included the 0.2. So I'm not going to put an equals to line on that value because then I'd have 2 values at -2 and that doesn't work. But then the next x value that I have a change in direction is when x is 0. So I'm going to say that goes until x is less than or equal to 0 because that's where my next turning point is. My last one, again, is 4. It has to start at 0. Only this time since it's going to continue on forever, I'm going to write x first, and then it's going to be greater than 0 because it's all the values that way on. So my last value is when x is greater than 0. So now I need to come up with my rules. So if I start with this one, I see I went if I started here, I had a slope of 2, so I went up 2 over 1 in this section. So I know my slope is 2 and it's going up, so it's a positive slope. So I have 2x, and now I need to figure out where the y-intercept would be. So if I went here, I went up 2 over 1, I'm at -2. So I'm at -2, 2. So if I go up 2 over 1 again, I'm going to be at 4, -1. Go up 2 over 1 again, I'd be at 0, 6. So 6 would be my y-intercept value. I just had to reason through that a bit so I could count. I know on your graphs you could do a better job counting it visually, but since I don't have the full graph, I was imagining going up 2 over 1, up 2 over 1, and I'd be up at 6. So I know my y-intercept is 6 for that, even though it's not included on my graph. The next rule, again, I went down 2 over 1, down 2, so it's a negative slope, but it's still 2. It's going to be -2x, and my y-intercept I can see is -2, so it's -2x minus 2, because that's where it crosses the y-axis. So then I know that's my rule for the second one. My last one, I go up 1, 2, 3 over 1. It's again a positive slope, it's going up from left to right, so I have 3x, and my y-intercept was still -2 because they were both at that point. They both started at that space. So 3x minus 2 is my last rule. All right, I know that can be kind of tricky. We'll get a little bit of practice with that in class, but the last thing I want to mention are the two last vocab words I mentioned in our language objective, step function and greatest integer function. So a step function pairs every number in an interval with a single value. And it's called, so what this ends up looking like is steps. So a step function is called a step function because when you graph out that, it looks like a step function. So one type of step function is called the greatest integer function because it is only interval values on the function. The way you write this is f of x equals brackets around x, that's the parent function, and the graph itself looks like this. So I have my x-axis, my y-axis. You have 1, 2, 1, 2. You have a closed circle at 0, an open circle at 1, and then a flat line between. So if I assume this is the next two values, you have, again, a closed circle at the next whole number, and then an open circle between, and then the values between that stay at that point. And then it looks the same in the negative side. So it ends up looking like steps because everything between, when x is between -1 and 0 is going to be -1. Everything between 0 and 1 is going to be 1. Everything between 1 and 2 is going to be 1. Sorry, that was 0, 1. Everything between 2 and 3 is going to be 2. So you can see that it's always going to be an integer value as your output. The last thing I want to say is this is going to be important. For example, if you want to mail a book, that is 3 pounds. And I want us to use the graph I'm going to draw here. So I have a graph here that I'm drawing. This is the price to mail. This is one in dollars. 1, 2, 3. 1, 2. This is the pounds of the package. So this is again 1, 2, 3. So if it's from 0 to 1 pound, it's going to cost $1. From 1 to 2 pounds, it's going to cost $2. From 2 to 3 pounds, it's going to cost $3. So, and then from 3 to 4, if I drew that last one, it would cost $4. So since it's 3 pounds, that the filled in dot here, that's an open circle, sorry, is going to be at 3, so it would cost $3 to mail that package. So these sorts of situations arise in situations like this. All right, make sure you write down any questions, comments, concerns you have so we can go over them together in class.